Okay, question came up about the arc length of a linear function. A function whose x and y parametric equations, whose x and y values are both linear functions of a parameter, of the common parameter. And of course, if you eliminate t from either of these and substitute into the other, you see that you get a linear function. Okay, if x changes at a constant rate and y changes at a constant rate, then in any time interval they'll both change in the same proportion, which is going to lead you along a straight line. And you should understand that. But formally, to get the arc length, you form the vector from dx dt, which is the rate at which x changes with respect to t, and dy dt, which is the rate at which y changes with respect to t. Now that vector is going to then be, well, dx dt is a change in the x direction, so that would indicate a change in the direction of the vector I. So we have dx dt times I, that vector, the vector dy dt times j, and that vector tells us at what rate we're changing position in the plane, or if we have k components, also in space. Okay, well, that then is the rate of change of our position with respect to time. Okay? And of course our position vector is just what? It's x of t times I plus y of t times j. So this is just the derivative of our position vector with respect to t. And we can regard that, if we regard t as something that changes in time or something that could be changed in time, we could regard that then as a velocity vector. Now the arc length we get by seeing how far we move along this curve. If we regard t as time, that means the arc length is going to be what we get when we integrate our speed with respect to time. Our speed is the magnitude of our velocity, so this is the magnitude of our ds dt vector. And if we're looking for the arc length on the interval from t equals e to t equals f, then we're going to integrate this speed with respect to time, because integrating speed with respect to time, an average speed multiplied by time interval is going to give you how far you've moved. We integrate that from e to f, from t equal, between the two values of t. And of course, the magnitude of our ds dt vector is just dx dt quantity squared, the square root of the quantity dx dt squared plus dy dt squared. And in the case of these parameterized x and y coordinates, that's just going to be, well, dx dt is just a, dy dt is just c. That's going to be square root of a squared plus c squared with respect to t. Excuse me. And that's just constant. A is just a constant number, c is a constant number. So since we're integrating a constant, we can bring that outside the integral, and then the integral from e to f with respect to t is just f minus e, and there we have it. And that's just the square root of a squared plus c squared times f minus e. Now, f and e are the two values of t, the final and the initial values of t, so that f minus e is just your time interval, and this is just the magnitude of the ds dt vector, which is a magnitude of what we could regard as velocity vector. So we have a constant speed for a certain time, we multiply that, we get our distance. And in the case of a linear function that's parameterized by linear functions of the parameter, that becomes very simple. But even if it wasn't, even if we had a different function here, we'd easily be able to get the dx dt, the dy dt, square it, take the square root, and then see if we can integrate that. Now, as you are aware, many times you get expressions that you can't integrate. And in that case, you of course go to approximation techniques. Okay, well that illustrates our thinking about an arc length, and it illustrates how it simplifies greatly for a function that gives us a straight line. especially a function that's given where the x and the y are both linear functions of the parameter.